So continuing to talk about separation of variables, we're going to talk about something called homogeneous differential equations. Homogeneous differential equations are ones that we can separate. The problem is sometimes we can't separate it with what we're given. So we have to be able to change our variables some way to make it separable. So why go through all the work of separating and changing the variables just to find out it doesn't work anyway? So to avoid that, we will always first check to see if it is homogeneous, and if it is, then we'll go through the work of actually changing the variables and making it separate. So to determine if something is separable and homogeneous, I need to see, does f of tx ty equal t to the n f of xy? All that's telling me is if I plug tx in for x and ty in for y, do I get, after doing some simplifying and some factoring, do I get t to the n f of xy back? If I do, it's homogeneous and it's to the degree n. So if I look at my first example, I'm determining if my given function is homogeneous, and if it is, I'm going to figure out what degree. So all I'm going to do is I'm going to plug in f of tx ty. So every time I see an x, I'm going to put tx in its place. Every time I see a y, ty. Giving me tx squared times ty minus 4 times tx cubed plus 3 times tx times ty squared. I can go ahead, since it's multiplication, and distribute my exponents, giving me t squared, x squared, ty minus 4 times t cubed, x cubed plus 3tx times t squared, y squared. So what did I do? Distributed this x squared, dropped these parentheses, they weren't necessary, distributed my cube, dropped these parentheses, they weren't necessary, and distributed my square. From here I can multiply my t's, and I can multiply my t's, giving me t cubed x squared y minus 4t cubed x cubed plus 3t cubed xy squared. Well, because every single term has a t cubed, I can factor my t cubed out, leaving me with x squared y minus 4x cubed plus 3xy squared. Well, let's compare this to my original function. I have t to the n out front. I have x squared y on the inside, minus 4x cubed on the inside, 3xy squared, 3xy squared. So notice I have t to the n, t to the third, times my original function. So yes, it is homogeneous. My degree is 3. Degree 3. So looking and doing the same with the second example, all I'm going to do is go ahead and figure out what is f of tx ty. Plugging ty in everywhere I see a y and tx everywhere I see an x, I get ty times e to the tx over ty. I can't write small enough to do a fraction as an exponent. Plus ty times sine of ty over tx. And now from here I simplify and clean up anything I can. So I notice in my exponents here I can cancel my t's. Giving me ty e to the x over y plus ty sine of y over x. Because both of my terms contain a t, I'm going to go ahead and factor that t out, leaving me with y e to the x over y plus sine y over x, closing my outside bracket, my outside parenthesis. And notice that inside here I have my original function. Outside I have t to the n being 1. So again, it is homogeneous, and it is degree 1. Looking at my next example, example C, doing the same thing because I'm still answering the same question. What is f of tx ty? This would be a good one for you to try, this one and then possibly D as well, so you can see if you're catching on to this. Giving me tx plus ty squared. I have to put that in parentheses because I'm going to have to distribute the square in. giving me tx plus t squared y squared. So I notice I can factor out a t, giving me x plus ty squared. Because of this t, I was not able to rewrite this as t to the n times f of x, f of y. I have an extra variable in there, so this is not homogeneous, which means I do not have to worry about the degree. And looking at the final example on this, and there's one other thing I want to point out. I have f of x equals x over y. So what is f of tx, ty? Well, it is tx over ty, which reduces to x over y. Notice that even though I might look at this right away and go, well, there's nothing to factor out, it must not be in that form, I know that nothing is really the same thing as 1 times something. And 1 is the same thing as t to the 0. So this tells me it is homogeneous and the degree is 0. And then the last thing I want to talk about with this is the definition of a homogeneous differential equation. So this is the actual definition we need to know or need to be aware of, is that a homogeneous differential equation is an equation of this form. So some function dx and some function dy, where m and n are both homogeneous. The reason that's important is we need to have all of our x's and our dx and our x function on one side, and we need to be able to move our dy and our y over to the other side. So if I looked at just this one example, and I wanted to determine if this was a homogeneous differential equation, I'm going to say that my m, x comma y, I guess, if I follow my formula a little bit better, is x squared plus xy dx. So I need to determine, is that homogeneous? So using that same concept that I just used, I'm going to check, does m tx ty give me t to the n xy? So I'm going to plug in tx for x and ty for y. And notice that it gives me t squared x squared plus t squared y squared, which does factor t squared out. Whoops, I don't have a y squared there. I misread my writing. That's an x and a y, so it's t squared xy, which gives me here, after factoring out my t squared, I can't erase that y squared, I don't know why, x, y, dx. So notice that I do match there, so this is homogeneous. If I check the n of y or n of xy dy, I notice that I have n of xy dy equals y squared dy. Doing the same check, that gives me ty squared dy, which gives me t squared y squared dy. That's not a y. Man, I'm struggling. Dy. Then notice that I do in fact match up with what I was given with some t squared. They have to be of the same degree. So this one was of degree 2. This one is of degree 2. So looks good. So this would be a homogeneous function. And that is it.